In this video, we're going to talk about the signals that are the most important for this course. Uh, we're going to see these signals over and over and over again. One you've already seen already is the sinusoid, and signals that are basically related to the sinusoid in some way. Well, then we'll talk about a very different class of signals. They're pulse-like signals. These you haven't seen in your calculus course. These are going to be interesting signals, as you'll see. But probably the most important thing in this video is the segment on how to think about signals, how to build them, and how to think about them as simpler parts. That's going to be a very, very important thing we're going to talk about. So, here's our sinusoid, and we've seen it before. As we've said, it has an amplitude A, which determines how big it is. So this negative part down here has a size of minus A, goes down to minus A. The frequency determines how often this reappears. This is a periodic signal, which means it repeats. And it's certainly clear that if you hop over to the next peak, you're going to get the same signal back again. Whatever occurred here is going to reoccur here, is going to reoccur here, etc. Well, the period we call capital T, and it's just a symbol that we'll use often for what the period of a signal is. How is it related to F naught? And if you think about it for a second, the sine wave repeats whenever F naught times T is an integer, which means that T has to be 1 over F0. So F0 again is the frequency in hertz, and this formula gives T in seconds. So hertz has units of inverse seconds, if you will. And then finally there's the phase, which basically defines how this starts at the origin. So that value right there is A sine of phi. So if phi is 0, this thing starts at 0 at the origin, and therefore there's no what's called phase offset. Now I should point out that if you have cosine 2 pi f naught t, it's another sinusoid, that's equal to a phase shifted sine wave. When it's shifted by 90 degrees, pi over 2. You should verify that formula is correct. I hope I didn't make an error, but I think it's right. And therefore a sine wave can be written in terms of a phase shifted cosine also. So there's really no difference between a cosine and a sine. They're phase shifted versions of each other. So this is what phase does. It moves things around in time. Now, the next signal we're going to talk about is the complex exponential. Yes, complex valued signals. So J here is the square root of minus 1. And this signal is incredibly important for us. It's incredibly important for all electrical engineers. This is another periodic signal. Its period is the same as the sinusoid we saw before, and its period is equal to 1 over f naught, 1 over the frequency. Now you can plot this in the complex plane. So this is the real part. This is the imaginary part. And it turns out that it goes around in a circle. So if you the angle at any one time is 2 pi f naught t, whatever time is. So as time increases, this angle increases, and this complex exponential looks like an arrow that goes around and around and around the unit circle, and the time it takes it to go around once is the period. That makes it periodic, and I think it's pretty clear, again, that that period has to be such that f naught times t is an integer. That makes the period 1 over f naught. Now, I hope you all know Euler's relationship, which says that a complex exponential actually consists of a cosine and a sine. So the cosine is the real part of the complex exponential, and the sine is the imaginary part of the complex exponential. I cannot stress how important these signals are in our course. So, in particular, the complex valued nature of it is very, very important to understand. So if you're a little unfamiliar with complex numbers, Euler's formula, I suggest you look at the complex numbers video, which I've made. I hope it will help you develop a better mathematical appreciation of complex numbers and complex valued signals. Okay, let's go on to our pulses. Pulses are going to be a little different than what you've seen in calculus courses because most of them are discontinuous. You probably shied away from discontinuous functions in your calculus course, but pulse signals occur all the time. And perhaps the simplest signal is what we call the unit step. It's equal to 0 for t less than 0, and then it's equal to 1 for t greater than 0. So it looks like a step up, where it gets its name. Now you probably noticed right away I didn't define it at the origin, and that's just the way it is. Its value at the origin is undefined. Turns out it doesn't matter what its value at the origin is, and you may not like that, but get used to it. It turns out it's going to occur all the time, and it turns out we don't really care what the value is at the origin. It just plain doesn't matter. So, another signal that has discontinuities is what we call the unit pulse. And by the way, the word unit here refers to the fact that the amplitude of this pulse, the amount it jumps, the size of its discontinuity is 1. So the amplitude of this pulse is 1 because it's a unit pulse. So, as the formula says, it's 0 for t less than 0. It's then 1 in between 0 and delta, and delta is called the pulse width. And then it's 0 again afterwards. So it pops up, stays constant, then goes down and continues on. So that's a single pulse. We're going to discover that the pulse is used very frequently in digital communications. It's used to represent bits. That's what makes it extremely important. And the next signal we're going to talk about is the square wave. So a square wave is a periodic signal, has a period of capital T as I've labeled it here, because you can see it repeats every capital T. It goes on forever. The amplitude of a square wave is, there is no convention for that. We don't really talk about the unit square wave. You explicitly have to give the amplitude, which I've just labeled here as A. So it has discontinuities at the origin t over 2, t, 3t over 2. So it's discontinuous every t over 2. And what its value is at those points just plain doesn't matter. It's discontinuous. We'll just have to appreciate that as we go through the course. All right, here comes the good stuff. Here comes the part that's very, very important. We have to build signals. What do we mean by that? the thing we have to first talk about before I get into building signals is what's called a signal delay. So here, the delay is tau, and I claim this signal is delayed in time by tau. So let's see how that works. The example I like to use is a unit step, because this point of discontinuity gives us a handle to latch on to where the origin is in the signal. So I'm going to pretend that my signal S is a unit step. So here it is, just U of t, just like we've seen earlier in this video. If I delay it, I claim it looks like this. So let's see if we can figure this out. The discontinuity occurs where the argument of u is 0. So argument u is still a function. It's now 0 when t equals tau. That's where the discontinuity is. So this means that this formula right now corresponds to a step that's been delayed, shifted over in time to tau. So u of t plus tau is called a signal advance. That means this discontinuity now occurs at minus tau, wherever this argument is 0. So we usually think of tau as being a positive number, so that the sign in the argument here tells if it's a signal delay or an advance. But signal delay is going to be a very important thing in building signals, as you're about to see. So let's have a little game. Let's see if you can tell me what this signal is. So we have here a unit step and a delayed unit step. It's delayed by delta, and I subtracted the two signals. What does it look like? Okay, well, let's try to plot it. We'll plot the pieces. So the unit step, of course, looks like that. The delayed unit step is just as I've shown it already. It looks like that, occurring at delta. But we have a minus sign over here. So what does that do? Well, that inverts it, flips it over. So now it looks like that. So what's the sum of the red curve and the green curve? It's 0 out here. All we get is the red guy up here, and then when they subtract, the red and the green cancel each other, and we get that. Ta-da! What we have is the unit pulse. So actually, you can think of the pulse as being a sum of the unit step and a delayed unit steps. By sum is the same as the difference here. But it's the difference between a unit step and a delayed unit step. I've now decomposed the signal into what I claim are simpler pieces. I actually look at this pulse and I see those two components when I look at it. Let's try an example here to see how this works for a little bit more complicated case. So this thinking about signals as a sum or difference of simpler signals is called signal superposition. This word superposition is going to occur again and again here. So superposition means just to add them up. Okay? Here's our example. How would you build this? How would you deconstruct it? How would you think, what are the pieces that you see in this signal? Okay, well, what I see is I see that big discontinuity. Right away, the first thing that jumps out is that it's discontinuous. That tells me there's got to be a unit step in here somewhere. If we put in a unit step, a negative unit step because the step is going down, at the origin, of course, that's not the right place. We need to shift it over to 1. Well, as we've seen already, that's a delay. So we just move it over, and now we get a discontinuity at the right place. All right, that's good. But now we want to talk about this earlier part of the waveform. It looks like it goes up linearly with a slope of 1. How do we describe that? Well, we can describe that by what's called the ramp function. That's why I called it RT. And I want to point out it's the integral of the unit step. So a ramp function is 0 for t less than 0, and then it goes up with a slope of 1 forever. And that's the same as this integral. Well, okay, so now what do we got? If we add together the green curve and the red curve, let's see, we got this in this range. Oh, it's going to be 0 back there. There's no, the red curve is 0, so you get the ramp. And then you get a discontinuity because of the unit step. So it jumps down. The ramp is continuous. The unit step is discontinuous. That causes the discontinuity when you add them up. But it keeps on going forever because of the ramp. Well, that's not quite what we want. We want something that cancels this ramp part in this area, only in that area. What would you do? Think about that for a second. What signal could you add out there or subtract to make that part disappear? And I think you know what the answer is. The answer is a delayed ramp. So we now have our blue signal is that delayed ramp. And when you add them all together, you get the black curve. And so our final expression for S of t is that it's a sum, a superposition of elementary signals. It has a ramp delayed, and it also has a unit step. This is what I mean by signal decomposition. Signal superposition is building signals. Decomposition is thinking about the pieces. I would also point out that this ramp is built from a unit step. It's the integral of it. So basically this signal S, although it looks a little screwy, turns out is actually built from the pieces that build it are integrals of the unit step and the unit step itself. So the unit step is the key thing that's in this signal, even though this early part of the signal doesn't look anything like a unit step. It turns out it lurks underneath inside an integral. That's kind of cool. We're going to use this over and over and over again as we go through this course. Okay, so let's review. The important signals are sinusoids, and even more importantly is the complex exponential, it turns out. The real and imaginary parts of the complex exponential correspond to the sinusoid. We've talked about the unit step. Discontinuous signals are going to occur over and over again, both theoretically and in practice. Pulses are used to communicate bits, and as we've seen, a pulse can be considered as a superposition of unit step functions. So this construction in deconstructing signals is a sum of simpler signals. Oh, is this important? This is going to make your life easy in doing calculations. And I can't stress, it also helps you understand what is going on. We'll see this in the succeeding videos.